Good afternoon. My name is Martina Bodner. I'm a science teacher and I'm a secondary teacher to the Training and Educational Directorate of Bolzano in Italy. The presentation I'm sharing with you this afternoon focuses on a group of students who are too often overlooked, upper secondary students with dyscalculia. My goal is to show you that teaching chemistry to these students does not require a revolution of content, but an evolution of methodology. I will begin by introducing specific learning disorders, and then I will zoom in dyscalculia, and then I will move to mathematics, chemistry, includes textbooks before closing with key findings and recommendation. So let us begin with the foundation. What are specific learning disorders? Specific learning disorders, or SLDs, are a group of neurological conditions that affect a specific skill of the skill domain, while leaving the general intelligence intact. This is what makes them specific. A student within an IQ within the norm who struggle with reading, writing, or calculation. The four main types of SLD are dyslexia, which affects reading, dysorthography and dysgraphia, which affect writing, and dyscalculia, which affect numerical skills. Importantly, these disorders often co-occur, and we call that comorbidity. So a student with dyscalculia may also have dyslexia. How are SLDs diagnosed? The Italian Consensus Conference established the discrepancy model. Diagnosis requires two conditions to map simultaneously. First, performance of the affected ability must fall at least 2 standard deviations below what is expected for students' age or grade level. Second, the student's general intelligence, measured by IQ, must be within the normal range, that is at or above 85. In Italy, students with SLDs are protected by Law 107 of 25. This law is a cornerstone of inclusive education in our country. It establishes several key obligations. Schools must identify suspected SLDs and refer families to accredited diagnostic centers. Every teacher is required to prepare a personalized didactic plan called PDP. And students have the right to compensatory tools and dispensatory measures. Crucially, the law acknowledges the risk of exclusion, frustration, and lasting impacts on employment if SLDs are not identified and supported in time. So this is simply not an educational issue, it is a social equity issue. So let us have a look more closely at dyscalculia. Dyscalculia is a specific disorder of the basic ability to understand numbers and numerosity. Most people are born with what researchers call numerical intelligence, which is an innate capacity to mentally manipulate quantities, and it depends on specialized brain circuits. In students with dyscalculia, these circuits function differently. The Consensus Conference distinguishes two specific profiles. Profile A involves weaknesses in the cognitive structure of the numerical components, so difficulties with quantification, comparison mechanism, and mental calculation strategies. Profile B involves weaknesses in executive procedures, which is difficulties in reading and writing numbers, retrieving numerical factor, and executing written algorithms. Most students have presents elements of both profiles. Numerical intelligence develops in stages from birth. By age 2, children have pre-verbal knowledge of quantity. Then, between 2 and 4, they acquire numerical words and counting skills. reading and writing numbers develops between 4 and 7. From age 7, strategies are refined and basic operation stabilized. Students with dyscalculia tend to remain stuck at early stages. The inability to memorize multiplication tables, transposing digits, forgetting to carry on in division, these are not signs of carelessness. These are signs of a neurological. And as these difficulties accumulate, so does the impact on the student's self-esteem. And these bring us to mathematics. Effective mathematics instructions for students with dyscalculia rests on several key principles that differ significantly from traditional approaches. The first one is reason understanding over rote memorization. Instead of asking students to memorize the arithmetic factors, we should build conceptual understanding through reasoning. This means using concrete materials, drawings, diagrams, graphs, to make abstract concepts more tangible. The second principle is proceeding in small steps, limiting memory load and offering sufficient repetitions. The third is active participation, games, open-ended questions, varied activity that allows each student to find its own solution pathway. Instructions must be clear. Font and line spacing should be adapted for readability. Where possible, the meaning of symbols should be stated explicitly near the symbol itself. One of the most important aspects of working with students with dyscalculia is understanding the emotional dimension. As you can see from this slide, the failure experience in mathematics does not stop at a cognitive level. It creates what researchers call the low self-esteem spiral. Repeated failure leads to frustration. Frustration leads to anxiety around math and other STEM subjects. Anxiety leads to avoidance, and avoidance leads to further gap in learning and therefore more failure. Once a student enters this spiral, it becomes very hard to break it. But we have strategies, cooperative learning, ICT tools, and also the strategic use of biographies of scientists who overcame similar challenges. So, for instance, Albert Einstein began speaking very late in life, yet he won a Nobel Prize in physics. Thomas Edison had a lifelong difficulties with spelling and arithmetic, but he gave us the light bulb. Vera Rabin described her own teacher, the physicist George Gamow, as someone who could not write or count, and yet she said his mind was capable of understanding the universe. Werner von Braun had severe difficulties with numbers, yet he found it awesome. So presenting these biographies normalized neurodiversity and transformed the narrative from I cannot do math or science to I can do math or science differently. So let's turn with a specific challenge that dyscalculia creates in chemistry. Chemistry is in many ways a perfect storm for a student with dyscalculia. It combines logical thinking and sequential reasoning with extensive numerical calculation, unit conversion, and the memorization of a large vocabulary of formulas and notation. So one issue that often goes unnoticed is formalism inconsistency. Take the concept of moral mass and molecular weight. Both represent the sum of atomic masses, but they use different units, different symbols, and also are named differently among textbooks. Molar mass is represented as MM or M. And molecular weight in Italian textbooks appears as PM, peso molecolare, which is the literal translation, but also MW, so with the initial in English. For a student who already struggles with numerical reasoning, this ambiguity increases the cognitive load. So the study of Kaminska, Ostep, and Bulimska provide us with some of the most concrete evidence we have for inclusive chemistry pedagogy. The study involved 400 students between 13 and 15, approximately 20% of whom had dyslexia or other SLD. So each class was divided into two groups, homogeneously matched for SLD and non-SLD students. One group received method A, so the traditional chemistry approach. The other group received method B, the inclusive one. The results through 4 didactic units are shown here. So just to make some examples, the first innovation concerned computational chemistry, so stoichiometric calculation and unit conversion. The traditional approach uses algebraic equation, which requires students to hold multiple variables in working memory to manipulate them algebraically. The inclusive method is the proportion method, and it replaces the traditional method with a simple structure. A is to B as C is to B. This breaks the problem into a single management relationship. Again, video instructions for laboratory experiments replaced written protocols. The benefits are obvious. A student can pause, rewind, and replay at its own pace. And multisensory input, so seeing and hearing the instruction, rather than just reading them, reduces the cognitive load. What is important to notice is that not only SLD students benefit from these innovative methods, but also non-SLD students. So it's something that is useful for the whole class. What is more interesting is the second part of the slide, because the traditional approach is the ball and stick model, while the innovative approach is the animated computer models for organic chemistry. And here, the study found out that the traditional model, so the ball and stick, outperformed the video animation. Why? Because direct hands-on manipulation promotes meaningful learning, building genuine understanding of the molecular structure. And just as in mathematics, also in chemistry, it's very important to sustain self-esteem. So again, some examples. Carol Greidel discovered telomerase and won the Nobel Prize in Medicine, and she had dyslexia. Jacques Dubochet, who received the Nobel Prize in Chemistry for cryo-electron microscopy, had dyslexia. Archer J.P. Martin, inventor of partition chromatography, had dyslexia. Benjamin Franklin wrote his life about his math difficulties, so perhaps it was Dyscalculia, and yet he discovered the electrical nature of lightning. And so again, these are not stories about overcoming disabilities. They are stories about learning differently. And that refrain is everything for a student who would believe that his or her difficulty with numbers means that he or she cannot do science, math, or BS. And here is another example on how to use the periodic table in a different way. So some elements are highlighted because they were discovered by disabled scientists. So here we have blind scientists, scientists with progressive spinal disease, scientists with speech disorders. Again, the disability and the diversity is normalized. And so let's turn to two further tools available for chemistry teachers: inclusive textbooks and ICT tools. Among Italian publishers, Zanichelli has invested most seriously in inclusive designs. An example I want to give you is the chemistry textbook by Tupi and colleagues called Chimica, Molecole in Movimento. The textbook comes in 3 volumes, so the main volume, the lab book, and a booklet called Idee per imparare, so ideas for learning. And this volume is specifically designed for with SLD students in mind. It is bound on the short side, this side, which is something peculiar, but it's a choice because it reduces the visual complexity of the page. And also it uses a range of inclusive design features. So I want to give you an example of that. And it is the unit of the mold. In the main book, this unit is covered in 25 pages. In the booklet Idee per imparare, it is covered in 7 pages using concept activating maps, color coding units of measurement, and guided exercises with explicit step-by-step instructions. Moreover, what is really interesting is that it introduces the concept of Avogadro numbers using X, so something that is very concrete, everyday life. And it returns this analogy over and over. For a student with dyscalculia, this structure is not simplification, it is scaffold. And both the book and the booklet are available in the digital format with linked video and also in the audible form. So let me now bring together the rest of this presentation. The evidence points clearly to one direction. Inclusive chemistry teaching is not a compromise on the content, it is better teaching. Inclusive methodologies produces an efficacy gain in all students, not only in SLD students. Inclusive textbooks with mind maps, guided exercise, and everyday analogies reduces the cognitive load. Self-esteem intervention, like using the biographies of scientists, addresses also the emotional dimension that it is so often neglected. Each of these innovations, as said, benefits all students, and this is the principle of universal design for learning, improving the experience of learning for everyone. Finally, I would like to offer 4 recommendations. First, teacher training in multisensory pedagogies should be a standard component of science teacher education, not an option. Second, we need advocacy for equitable access to STEM subjects. PDP in chemistry should include subject-specific intervention, not a generic measure. And ICT tools should integrate it as standard element of including practice. At the same time, I want to be honest with the research gaps. Most studies on Dyscalculia focuses on primary mathematics. There is very little literature on Dyscalculia in upper secondary students, both in math and in chemistry field. We need longitudinal studies and we need chemistry-specific intervention research. This is an open field, and I hope some of the researchers in this room will be inspired to work on it. So thank you very much for your attention, and I'm happy to take questions.